Okay, so let's have a look at homework 10, seeing as we didn't really have a chance to talk about it in class. And I'll go through and give you a couple of hints on each question. So for the first question, because the conclusion is a conditional, obviously conditional proof might be the way to go. Now, if you're going to do conditional proof, you're going to fairly quickly assume A, because that's the antecedent of the conditional you want to prove. I say fairly quickly because actually, if there's a couple of things you can do first before you start assuming, then maybe it's worth doing. And actually, there is a couple of obvious things you can do, because if you look up here, you see that that's a conjunction in this funny font, that's an ampersand. So obviously that means you can simplify both sides. And in fact you are going to need both sides. So you could simplify E and then you could simplify not U. Then assume A. So let's say you do that on line 6. Obviously you indent and you write A S for assumption. Now let's hope that's going to be useful. Otherwise there's no real point to doing a conditional proof. And it turns out that A shows up here in the antecedent of a conditional. So you would be able to do modus ponens if you had the other part of the antecedent. Oh, and guess what? You do, given what you've already done. So you can get A and E, and then you can do modus ponens, and that's going to get you, by line 8, not I if and only if O. Now we need to remember that's going to be by modus ponens 1, 7. Now we need to remember our ultimate goal, which is, having assumed A, our last indented line, let's say on line 20, be pessimistic about this, is going to be Z, however we get that. And then we're going to go back to the real world and we will have proved if first indented line, which is A, then last indented line, which in this case is Z, by conditional proof, in this case 6 through 20. I'm not sure, it shouldn't take you 20, but that's just an example. Okay, so that's the overall structure of this thing. Actually, maybe it does take 20, but each step will be fairly straightforward. No, I don't think I'll take 20. Anyway. The tricky part, though, is here. Now you've got a biconditional. Now, why are you interested in something involving I and O? Well, for one thing, something involving I and O shows up here, and that'll get you, if you have the antecedent of this, you'll be able to get Y and Z, and then you'll be able to get Z by, so if you end up with Y and Z here somehow, you will be able to get Z by simplification. Line 19. So that's obviously something to hope for. To try, because you want Z, you need to get this in order to get there. Okay, and this is going to help you do that. But a word of warning. The only thing you can do with this is biconditional. So you're going to want to do biconditional. Yeah, now what you're doing is biconditional to this part. So this part in parentheses is equivalent to if I then O, and if O then I. Okay, that would be nice if that was all there was, because then you could simplify one of the sides. But actually that wouldn't really be ideal for you, because that's a tilde there. That's not going to be the immediate answer. Besides which, the rest of the line stays the same. So you have to have parentheses around that whole thing. And that's what you got by bicon 8. And then if you get rid of those parentheses, it's going to be by something like De Morgan's law, and you're going to have something like this. Because De Morgan's law means you get rid of this outer parentheses, you distribute the tilde, so there's 2 tildes, and crucially, what was an and becomes an or. That's by De Morgan's law 9. Now, that is what you want. Because if you have that, it's the same as this, and you can do modus ponens and get this by modus ponens for that, involving that and up here, and that's great. But the trouble is, this is a disjunction, and you need to get the negation of this side. So remember, the negation of this side is not if O then I, which is actually if O then I. So you need to have that to do disjunctive syllogism, which is going to give you this side, and you're going to do modus ponens. I will tell you, you can get something that is equivalent to this using not you. And that's the end of my clues for question 1. All right, question 2. Now there are 2 ways of doing question 2. Obviously, actually both of them. Having said that, you could do that by reductio ad absurdum. It's perfectly possible, and I'm sure you would be able to do it, but it would probably take quite a long time. If you did that, then what you would be assuming is the negation of the conclusion. So you would assume the negation of this whole thing. So the negation of if P, then if M, then L. And then that would be assumption reductio ad absurdum, and then I would advise you to do a couple of imps, which would give you P and not if M, then L, by implication, and then that would be equivalent to P and M and not L by another implication. So that would give you a fair amount to work with. It would give you P, it would give you M, and it would give you not L. And remember, your goal in reductio ad absurdum is to get, say, P and not P, or M and not M, or L and not L, any contradiction. So it's perfectly possible to do it by reductio ad absurdum, but I think it's probably easier to do it by conditional proof. Now, having said that, there's 2 ways to do it. One way is to do a double indent. We did one like this in class. So you start by assuming P, and that's single indent, and then you and the idea is to get down here, say on line 20, if M then L, and then you will have proved if first indented line P, then last indented line M then L, by conditional proof 4 through 20. Okay, but then the trick is you have to get if M then L, and because that is also a conditional, you can get that by conditional proof. So you would indent again up here, assume the antecedent, which is M, and then your last double indented line would be L, and then you would have proved if M then L by conditional proof 5 through 19, all the double indented lines. So this would be one conditional proof to prove if M then L, nested within another one that proves if P then if M then L. And actually doing it this way is fairly straightforward, because you can already use P modus ponens there, and once you get M you can do modus ponens there, and then you will have both of these, and then if you look at that you can kind of work out what you need to do. Alternatively, you can just assume P and not double indent and hope that you get, and actually there should be, it's tricky. That's probably the better way to do is like this. Alternatively, you could notice that this is actually equivalent to P and M then L by exportation. So instead of line 4 being assuming P, you could have line 4 be assume P and M, and then your last indented line, let's say line 15, be L, and then line 16 is I've proved if P and M then L by conditional proof 4 through 15, and then line 17 would be to do exportation, and you have if P then if M then L by exportation line 16. So that's an alternative way to do it that is just single indented and exploits the fact that this is equivalent to that by exportation. I think either of those ways are fairly doable. Okay, so that's question 2. Question 3. Oh, there's a nasty smudge on my table. Okay, with this one, I think reductio ad absurdum is the best method. Now, as you probably remember, if you were in class today, we reductio ad absurdum, because you want to prove u, you start by assuming the negation of that. So you assume not u, and then you say ARA. Now the nice thing about this is having not u is going to be immediately useful to you, because you can use it in both line 2 and line 3 with modus tollens. But do remember that when you do modus tollens, you end up with a negation of the antecedent. And then actually you will have things, so you will end up with like not Q or S for one of them, and not R or T. My suggestion is that you do De Morgan's law to both of these, and then you will have things to simplify. And eventually you'll be able to have Q and not Q, as, or possibly S and not S, or possibly R and not R, or possibly T and not T. Any one of those as your last indented line is a contradiction, which would then mean you could go back out, say this is line 19, you would go back out to the real world and you would say, okay, because I assumed not U and it led to a contradiction, then that means that U is true by reductio ad absurdum 5 through 19. So that's that one. Question 4. Let's see. Question 4, yeah, this one I think is actually fairly straightforward. You're going to use a fair number of rules of equivalence, and I will get you started. Obviously, if you did this conditional proof, assuming A, you would assume A and then try and get Z. Now A shows up here. Unfortunately, this is a biconditional instead of a conditional. If it was just a conditional, then you could do modus ponens. However, in a couple of steps, you can convert this into a conditional by doing bicon, which is the only thing you can do with a biconditional. So if you do bicon line 1, that becomes if A, then if B, then not C, and if B, then not C, then A. And then you just simplify this side, so that will give you if A, then if B, then not C. So effectively, in 2 steps, you have changed that into a conditional, which is good because then when you assume A, you can then do modus ponens, and it will give you if B, then not C, which is equivalent to the negation of that. And then you'll be able to do, or you can do contrapositive to that, so that this will be out the front, and you'll be able to do a series of modus ponens and things like that, and you will eventually get Z down here, and then you've proved if A, then Z by conditional proof. Alternatively, if that's not working for you, you can just assume the negation of the conclusion again. If not A, then Z. I'm sorry, if you assume not if A, then Z by assumption reductio ad absurdum, which by implication is equivalent to A and not Z. You know why I'm able to remember that so easily? It's because if you think what this is saying, it's saying that if A, then Z is not true. So it's saying that this conditional is false. What is the only time a conditional is false? When the antecedent is true and the consequent is false. So if you know that this is false, you know that A must be true and Z must be false, which means that not Z is true. So I know that not any conditional is equivalent to the antecedent and the negation of the consequent. And that's easy to simplify, and now you've got things to work with, and remember you're trying to get a contradiction if you're doing it this way. Okay, I hope that's enough to go on.